So the next part of the lecture is focused on optimizing the HIR, or the high-level intermediate representation of JIGS-RVM, the IBM research compiler and runtime system for Java. We've just gone over how we transfer or translate the bytecode programs that we have transferred over a network or to a target machine into this high-level intermediate representation. Our next job is to optimize the code to reduce redundancies and to make it as efficient as possible for execution. Our problem, however, is that we have to do this all at runtime. Most static compilers don't have the constraint of running at runtime with the program, so everything can be done ahead of time, and thus more time can be spent on the optimization itself. So we have to identify optimizations that are going to be very fast to apply and that produce great efficiencies. So most modern runtime systems with a compiler and an optimizer will perform these 5 optimizations: copy and constant propagation, dead code elimination, inlining, redundant check and load elimination, and common subexpression elimination. With copy propagation, the idea is to find a variable that is assigned to another variable name, and where both of those names are used in subsequent instructions. We don't need to use both names, and so therefore we're going to eliminate one of the copies. This frees up a name, which means it potentially frees up a register in the long term and makes the code more efficient. Constant propagation is similar. If there's an assignment of a constant value to a variable, we can instead use the constant variable directly instead of the variable name or the register in which the variable is stored. Local variable register renaming identifies when a name is used in multiple places, but where the names are not dependent or are unrelated. In this case, R1 in our example in the original intermediate code. R1 is used for the first def and second use. So the def in the first instruction is a define, which means that R1 is on the left-hand side of the assignment, which means that it is being written to. R1 in the second instruction is a use, which is a read from a register or variable name, and is on the right-hand side of the assignment. R1 is used again in another def in use that follows. These two sets are independent and thus can be named differently. By naming these differently, it tells ultimately the optimizer and the code generator that these code blocks or these two pairs of instructions are independent. And thus, if code is independent, we can move code around, reorder it, reschedule it to make it more efficient for the underlying architecture. Dead code elimination is an interesting optimization. The idea here is, in all of our other optimizations, we want to focus on the optimization itself to make the optimization as efficient as possible, again, because we're performing this all at runtime. So commonly we'll separate out the cleanup process, which in this case is called dead code elimination. Many of our optimizations will result in code that has no effect, either is not reachable or is code that produces no result. In our example at the bottom, we have a piece of code that we perform copy propagation on. Once we perform copy propagation directly, I find that the renaming of the register R1 results in an instruction that has no effect. R1 equals R1. So dead code elimination will come in and remove code such as this so that it's more efficient. We don't execute dead code. The next optimization that's common to these infrastructures and that produces significant performance gains is inlining. Inlining is the idea of taking a call from one part of the code that is invoking a function in another part of the code and replacing the call with the actual implementation of the function that's being called. There's a couple things that are happening here. First off, if we step back, all functions, when they're actually implemented, contain extra code that's hidden to the developer at the start of the function and at the end, right before the return. This is called the prologue and the epilogue, respectively. This code sets up the runtime stack, the system stack that holds our local variables and allows us to communicate arguments to parameters. And prologue and epilogue are also play a role in synchronization, locking, and in some cases garbage collection and threading. So this code could be significant. If the function itself doesn't do much, then the cost of the overhead for the prologue and the epilogue space-wise is not amortized. And so there's one way that inlining can improve performance is by reducing the number of prologues and epilogues that are needed. Because if this code is inlined, the only thing that's inlined is BB1 and BBN, or BB1 through BBN, and so the prologue and the epilogue go away. The other thing that's eliminated when we do inlining is the call itself, which is usually an indirect jump, or the return is an indirect jump, and sometimes the call can be as well. And both of these are place extra stress on the architecture pipeline under the hood. And so if we're able to inline code in this way, we're able to reduce two sources of overhead. However, we can't inline everything because that would cause tremendous code bloat, and code bloat can play and have a significant impact on performance. For things like register allocation, if we don't have very many registers to work with, but we have lots and lots of instructions, it's going to be hard to allocate data to those registers in a near optimal way. Also, code bloat impacts the memory hierarchy performance as well as the operating system page performance for the virtual memory system. So we have to trade off, this the benefits that we get from inlining with the downsides of inlining, and so it takes some intelligence to decide what to inline and when to inline. But if we can do it well, if we can do it correctly, and do it where there's large opportunities, the performance can be significantly improved. The next common optimization is redundant check and load elimination. With a language like Java, bytecode, the JVM language, or the .NET language, the Common Language Runtime, the Common Intermediate Language, CIL, from Microsoft's .NET framework, the stack-based machines move data between the local variable array and the operand stack. So there's lots of instructions that do this move. As you know, in Java bytecode, to move a value from the local variable array to the operand stack is an iLoad instruction. And a store does that in reverse, stores a value from the operand stack to the local variable array. The code has many of these instructions, and many of them are redundant. We'll load a particular local variable and store it somewhere, and then we'll load it again later. If the system can recognize that these are the same loads or the same variable uses, then we can avoid these redundant loads and hold things in registers. In this example, we can then perform copy propagation on the far right, which then can be followed by the dead code elimination to get a very efficient block of code. Similarly, these managed languages, have many checks that are inserted into the execution stream. These checks are things that the language provides to its developers for programmer productivity. For example, arrays. When you access an array with an index, the language itself enforces the fact that you cannot access off the end of an array. You must also always access within the allocated section of an array. Anytime you use an array, there's many checks inserted, and they're done many cases just blindly. Whenever there's an array access, we insert a check immediately prior. This simplifies the check insertion code, but it also leads to redundant checks. So in this case, we only need one check to cover both of the array accesses as shown in the figure. Similarly, in an object-oriented language that's managed, there's also many null checks. Every single time you access an object, either to invoke a method on it or to access a field through it, within it, there's going to be checks to ensure that the object that you're accessing is not null, because that would cause a memory fault. So again, we can insert these checks for null everywhere very efficiently, without much knowledge of the context, and then we can perform an optimization like redundant check elimination to get rid of the redundant checks as shown in the example. Once we have performed the 5 most common optimizations, some runtime systems will perform more, maybe some will perform less, but these are really the optimizations that give us the biggest bang for the buck. Now that we have an optimized high-level intermediate representation in the JIGSR VM, the next step is to convert this to the low-level intermediate representation. This is where we take instructions like the invoke static and the invoke virtual method call instructions and expand them into something that's more representative of what the underlying architecture can handle. At the same time, after we do this translation from HIR to LIR, we also can perform additional optimizations like common sub-expression elimination. Whenever you see an optimization and there's a keyword local by it, it means that the optimization is performed at the basic block level. Global optimizations are performed across basic blocks. Common sub-expression elimination identifies expressions in the code that are repeated, and we can use store the value into a register or into a name and use that name to represent that expression instead of performing the expression repeatedly. This is done in this LIR translation piece. Also done at this time, once we have LIR, is we generate a data dependence graph between all instructions within a basic block for all basic blocks. This is a graph of all the dependencies between instructions. They give insight to the compiler as to what instructions can move around what other instructions, because the goal of code generation is going to be to identify a sequence of instructions that's most efficient for this hardware. And given our pipelining of our modern architectures, we want to be able to reorder our instructions so that we can best take advantage of the features of a pipeline. So at this point in the translation process, we're going to generate all the data dependencies between instructions. There are 3 types of data dependencies: true, anti, and input. Another name for true is read after write dependency. A true dependency is where you have a use of a name, and that is followed by that follows a previous instruction that defines that register or name. So in our example, the blue arrows on the right between R1 and R1 and between R4 and R4 and 2 different instructions are true dependencies, read after write dependencies. Anti-dependencies are just the opposite. They're shown in the green arrow. This is where you have a def that follows an instruction that uses the same name. On the right, R2 is used in the second instruction and defined in the third instruction. So there's an anti-dependency, a write after read dependency for R2. Finally, there are input dependencies. This is where you have a read after read. In the example on the right, R2 is read in the first instruction and read again in the second instruction. So there is a dependency between these two. This is an interesting dependency because it can be used for different things, for different reasons. One way that this is used is in modern pipelines. If these instructions are both in the pipeline together, the data from the first instruction can be forwarded to the data in the second instruction, so we don't have to collect the data from R2 a second time. There's other optimizations that can be performed as well. Some are based on arrays. And again, once we understand all the dependencies between instructions, the compiler and then the code generator can reorder instructions to get the best performing set of machine instructions out of our code. Once we have all of this, we convert the intermediate representation to machine-specific internal representation. That is, we go from LIR, the low-level intermediate representation, to MIR, machine-specific intermediate representation. We still have, as we have throughout, just use and assume an infinite number of registers. These are called symbolic registers. We may not have this many physical registers in our machine, but we'll deal with that later. We then invoke a code generator, and typically compilers incorporate a code generator that is produced by a code generator. That is, there is software that's called code generator generators. This is software that produces code generators. This is a piece of software that takes a grammar for the intermediate representation, in this case MIR, and in this case MIR, that's right, and a grammar for the native hardware instructions of the architecture underlying, and uses something like dynamic programming typically to identify the best combinations of instructions for that architecture. So this code generator produces a code generator from these two grammars that we then can plug into our compiler. Once we have our MIR representation of our program, we have to convert the infinite symbolic registers that we use to physical registers. And we're going to do this with a linear scan greedy algorithm. Typically for register allocation, all register allocation algorithms in any compiler, static or dynamic, we first have to identify the live ranges for each of our variables. That is, another name for this is live variable analysis. And this is where we identify the range of instructions in which a register is used by those instructions. We typically identify the first assignment or the write, that is the def, and that starts the range, and the range ends at the next def of that register or the last use of the register if there's no next def. So given the code in the bottom, we can identify the live ranges for each of the registers, R3, R2, R1, R4. What we do is we draw the live ranges across the instructions from the first def to the last use or to the next def, and we see where there are overlapping live ranges. This overlapping live ranges means that the registers interfere with each other. That is, there are names that overlap that all need to be in registers at the same time if we were to be able to keep everything in registers. So in this example, you can see what the maximum amount of interference is. That is the maximum number of registers that interfere with each other. And in this case, it's 3. That is the maximum number of registers that you need to be able to allocate to this code optimally. For the linear scan register allocator, we don't have the time to put into identifying live ranges by making multiple passes over the code. So we're trying to determine the live ranges and allocate physical registers to these symbolic registers with a linear scan of the code. Our goal is to do this allocation of registers very quickly. At the same time, produce code that is pretty high quality. In order to do this, we're going to develop a linear scan register allocation algorithm. The way this works is it makes a pass over the code and identifies the live intervals for each variable. So the interval is represented by a pair in hard brackets, a pair ij, and I is an instruction such that there is no instruction I prime that happens before it for which V is live. We define J as the instruction J for which there is no instruction equal to or after this instruction J for which V is live. And of course, there may be intervals ij for which V is not live, and we can disregard these. We're looking for the maximal live interval. It may not be perfect, but it's going to be close, and it's going to be fast to discover. Any intervals that overlap is interference by those names. That is, those registers have to be in separate registers at that moment in time. The algorithm is given a fixed number of registers and a list of live intervals, and the goal of the algorithm is to allocate registers to as many intervals as possible, such that no two interfering intervals are allocated to the same register. If we have a moment in time where we have too many registers, too many symbolic registers, and not enough physical registers, then what we have to do is we have to spill the register, one of the registers, to memory. That is, we have to copy its data to memory so that we can use it for other variables. Every time we use that variable that we copied to memory, that data that we copied to memory, we have to read it back in, typically to a temporary register that only the compiler has access to in order to perform the operation. This is called spilling. We want to avoid spilling because it's extremely costly to move things in and out of memory when we use them. So for this algorithm, we said we identify the intervals and we store the intervals in order of increasing interval start. So the smallest instruction at which a symbolic register starts being live is how we're going to order this list. We're going to keep an active list at each step as we step through this array to identify which symbolic registers we have allocated physical registers to. This active list is represented by greater than brackets, and within those brackets are the names that are currently active. That is, the names, the symbolic registers that we currently have assigned to physical registers. This active list is ordered by from smallest to greatest live range end. So in this case, A comma B represents the fact that A and B are both active, that is, they're both in registers, and B's lifetime, B's live range, will end after A's. If the number of available registers is less than the number of things you need to put in your active list, that is when you have to spill to memory. That is, if the number of elements in the active list is greater than the number of available registers, we need to copy one of the elements to memory in order to get the data. Whenever we spill using this algorithm, whenever we copy something to memory, we do it for the rest of the method. That is, once we spill something, we will always spill it and read it and write it from memory every time we need to use it, even if there's many, many instructions that use that register going forward. We're going to decide what to spill by identifying the register with the longest interval end. That is, the variable that will live the longest, that will be alive across the most instructions going forward. This is just a heuristic, it's just a guess, but it works pretty well in practice. And what it's saying is, if I'm going to spill a symbolic register, I want to do it for a variable or a piece of data that's going to live for a long time, and therefore if it lives a long time, it's likely to interfere with lots and lots of other registers. So I'm going to spill that, so I'm going to reduce the amount of interference, and it's really easy for me to find the elements with the largest interval end, because I've sorted my active list in this order. So I just take the last guy on the list, and he's guaranteed to have the largest interval end, and we'll spill that one to memory, and we'll insert spill code for all of the instructions that follow this instruction to read in that value into a temporary register so we can perform the operations on it going forward. So here in our example, we have our sorted array of intervals by interval start. We begin our active list with our first instruction. And we're just going to step through the instructions along the bottom, 1 through 10. At instruction 1, element A becomes live, and so we're going to add A to our active list since nothing's in our active list. The number of available registers we have, by the way, is 2. So our active list at most can have 2 elements in it. We next proceed to instruction number 2, at which time B comes live. So we add B to the active list, and we put B after A because B ends at instruction 5 if you look at its interval, and A ends at instruction 4 if you look at its interval. And so we keep this in we keep this in increasing interval end order. Decreasing. So that the last element in the active list has the largest interval end. Next, we hit instruction number 3, at which time C becomes live. A, B, and C are still all live at this point. And so we add C to the active list, but we notice that the active list now is longer than the number of available registers we have. So we have to choose which element to spill. Because we keep them sorted, we know that C has the largest interval end, and so we remove him from the active list and we spill him to memory. Now we look ahead at all the instructions. Any instruction that uses C in the future, we have to read from memory into a temporary register to perform the operation. And when we're done, we have to write out any updates to that register back to memory. C will be spilled for the remainder of this method. Next, we hit instruction number 4. At this time, because of the intervals, A has ended. A's interval end is 4. This means that at instruction number 4, by the way we defined our intervals as greater than or equal to J, this means at instruction 4, A is no longer live. So now we just have B in our active list, and also at instruction 4, D becomes live. So we add D to our active list and make sure that they're in the right order according to largest interval end. We have to ensure that the largest interval end is at the end of our active list. We then proceed to instruction 5. At this point, B is no longer live, so it leaves the active list. We have E and D in our active list at this point because E has just become live at instruction 5. We order them E ahead of D because D ends later than E does. Once we complete register allocation, we just have a few other jobs left. The first thing is we have to generate the prologue and the epilogue for this method. We've just converted all the code for a single method, optimized it, and performed register allocation on it. Now we need to add a header and a footer to this method. The header is called the prologue, and the footer is called an epilogue. The epilogue must occur before the return is taken, before any return is taken in the method. The prologue and the epilogue are in charge with setting up and tearing down the stack frame, setting up and storing and restoring any non-volatile registers. These are registers that the caller is expecting to, hold a value consistently across the call. Other operations that happen in the prologue and the epilogue have to do with threading, which we'll explain in a future lecture, and locking for synchronization. The epilogue is also in charge with handling the actual storing of the return value and returning to the caller. Once this code has been added to methods, we store the method block into memory, into an array, and give it a home. We update our internal representation in our runtime system appropriately for the new method address, so that next time we call this method, we can jump directly to the native code and execute it at high speed without any interruption. Some things that I'm not mentioning here are, as at the very end, as I'm generating my last, generating the final representation of the code, we're going to insert some support for handling exceptions and for enabling garbage collection. That is, garbage collection, if you remember, needs to know where all the roots are at any moment in time, that is, at any instruction. So these maps are generated at this time as we're writing out the code in binary.